Okay, so in efforts to actually explain why I do my PID loops the way I do them, I'm going to actually build one from scratch basically, and it will be using the same controllers that I have. So in L72, we'll just call this PIDE explanation, right? Because realistically, I mean, it does need an explanation. So a lot of times what will happen, and we're going to use 32 because again it goes back to having the actual ability to use auto tune over 33. You cannot do it unless you have the license, and I do not have a license on this actual VM, but I am using slot 1. So I'm coming in here and if I pull up the right program, here we go. As you can see, I was looking at some Cartesian stuff. So let's minimize that. And that got me thinking about, I should go back and revisit the PID stuff. But anyway, so slot 1 is what we're using. We're not going to use any kind of protection or anything like that. We're going to come in here and open it up and start from scratch. I'm going to immediately change the task from continuous to periodic, because in PIDEs, the best way to, actually the only way to really get them right is to have a periodic task. So you can do it event driven, but that is kind of tricky stuff. So when it comes down to it, event, you got 3 different tasks, right? Periodic or continuous, periodic, event. We're going to use again periodic. So we'll put it like at 100 milliseconds, nothing crazy. Come in here, and I like to put this. For the newer versions, they actually do put this behind it, but for the later versions, like 32 and I think later, you actually have to manually put it in the name. So I put it in the manually put it in the name so I know, and then come over here and add my first routine. My routine is going to be obviously a function block because I am using a PIDE simulation, and this will be explaining why I simulate the way I do. So again, just breaking this down, just so very first I'm gonna come in here, put my JSR in, so I'll link my routine that I just added to the actual scannable program. And when I mean scannable program, you think about the task is already scanned, the main program is already scanned, and main routine is already scanned, because if it has a little page with a 1 on it, that's the main routine. So other than that, if you do not put a JSR, it will not be linked. So with that said, come over here and start building. I want to make sure real quick my settings are right for my wire, my flow, my window. I just like to make sure my colors are right. All right, so with this, we have our process, and we're going to pull down our PIDE. We're going to name this, let's just give it a name. Especially, I don't like the fact that it's going to give it a name in basically the actual program tags. I want to put it in the actual, I want to put it in the program scope, right? So you get 2 different scopes here. You got the main program, and you have the PID explanation, which is the actual main of the actual, this is a controller scope tag. So we're going to go ahead and actually, let's just name this PID sim. We'll just capitalize it, and then come down here, auto tune. You notice we don't have any auto tune tags, so we're going to make one. If it's just one, like if it's just one PIDE, something like that, then I'm just going to name it something generic, right? Auto tune. I could have just named it auto tune, and it would have been perfectly fine. Now it's not going to show it right here. It did make it though, so that we can come down here and select it. So that's given that, right? One thing that you need to be aware of, like there's going to be pins in here and stuff like that, that when you come in here to your parameters, you're going to see that are going to be defaulted, and you're going to see like different things like this that you can select, deselect, stuff like that. I don't really care about program cascade because we're not going to talk about that right now. Program override, we're not going to talk about that right now. We could leave it, to be frankly honest, which is not going to hurt anything, but we can, come in here and, not use it too. I'd rather get it out the way and not have it, kind of basically create confusion, if you would. So the operator request and the manual request is something that I will use when it comes down to it. So in the program auto request and the program request. Program auto request is already there, so that we're good here. So we've added this stuff in here. We could have taken out some of the stuff we're not going to be using, like the cascade. We're not going to be using cascade. So let's just take that out too, because we're not going to be using that. What else are we not going to be using? Feed forward. We're not going to use feed forward. And then, yeah. So let's kind of simplify this, if you would. We're not going to use ratio either, but we'll keep it in there for the sake of argument. So what we're going to do is we're going to put this to the side, and I'm going to show what I generally do when this situation. So I come in here, and we're in processes, right? So you have dead time is what they call it, and then you have lead lag. I like to put in dead time, and I like to put in lead lag. This is just for simulation, but I will say this: when you are simulating a PIDE, you can actually simulate it for the actual process that you're trying to tune. What I mean by that is, when you're tuning a PIDE, or you're trying to look at adjusting a PIDE, you have to know the mechanics of it. You have to know whatever devices you're using, whatever valves, pumps, flows, any kind of how long the pipe is, stuff like that. That's where this lead lag comes in place. And so for the dead time, you're going to have to create an array, right? So generally speaking, you'll create a pretty good size array. I just, for the sake of argument, just going to put 100. Right, so that gives it plenty of room. And for what we're doing, we'll just call this PID dead time array. And that way it gives you an understanding about basically what it's doing. Now, do you have to fill this array out? Like come in here and fill it out or something like that? What you do is you actually use it in here in your parameters, and you put your dead time in here. So in this case, we'll put 12 seconds. And then what we're going to do is tie the output of that to our lead lag. And for the lead lag, we'll put so you can either do lead, which means, well, let's just break down and talk about this, being that it does have the actual description. Lead is time in seconds, right? So the value of 0 disables the algorithm altogether. So if we leave it at 0, it disables the algorithm. The lag is basically saying, so this is going to be just like the name says, it's going to lag the process. You also have gain, bias, and stuff like that. I generally do not mess with that. I'll just put in 5 seconds for the actual lag. So in total, think about it real quick. I have 12 seconds plus 5 seconds. That's 17 seconds of actual delay, right? So this is going to tie into the PV. And then we're going to tie the CV EU, which is the control units, right? Engineering units that we're going to be using, right? We're going to tie that into the backside of the dead time. Okay, so what we need to do here, now the thing about it is, if I try to assemble this right now, it's going to fail, right? And it's going to do this, right? So the reason it did that is because you have to assume right here, you have to assume data availability. And now if I do it, it'll be fine. You see that? So just to kind of give you that clarity, if you're trying to backfeed if you're trying to backfeed or something like that, if you're trying to go back into the PIDE block or something like that, you're going to run into that. So again, when it comes down to it, I'm making this video to give a lot more detail. So this is not just going to be some, you know, here's how it was done. I'm going to show you exactly what I'm doing. So it will be a little bit longer, but again, as I stated in the beginning of 2025, the videos are going to be detailed, and it's going to be giving you exactly what you need to understand. So with that said, that's what we're going to be doing. Now, coming in here, we do need to put our engineering units in here. Okay, proportional gain, all that stuff we're going to get from tuning. Engineering units, we can just leave, currently, let's just leave them like they are. So the set point high limit is 100, although we can take it to whatever we want to take it to. Yeah, let's just say our higher limit for our set point was, for the simple sake of like what we were doing, was like I don't know, 500 or something. Like say you had a temperature of 500 that you were trying to, you know, that's your high limit and your low limit was 0. You could change that right here, and that's going to be based off the PV and the CV, right? So the set point limits are the set point limits. If you exceed the set point limits, or you are out of the set point limits, it will not work. Now the PV is basically your 0 and your 100. We generally leave that just like it is, for the simple fact of, you know, keeping things simple. CV again is the output, again keeping it simple as possible, 0 to 100. Okay, so with that said, we'll go ahead and add some auto stuff too. So we'll say we'll add a tag in here, and we'll call this PIDE in auto. And we want to change it from a dent to a bool because we're using a bit. And I'm gonna toggle this bit. I'm not gonna you know, have controls. I'm not gonna have a panel view or nothing like that, or any kind of things like that attached to it. What I will do is again tie this into the program and the program auto, and then I'll take the negative of that, which is a not, and I'll come back here and say if it's not in auto, then I want my operator request and my operator manual request. And this is going to basically give me the ability, because when you're tuning, when you're going to be tuning, you're going to need to put it in manual, and that just gives it that stability. So when you're tuning, just know that you're not going to be in auto. And there are some differences, right? If you're using specialized controls, say for instance like a plant PAX or something like that, it's completely different. But we're talking about a PIDE, okay? PIDE, even if it's using in a nested thing like gems or something like that, it's a little bit different. So again, so we're going to put our controls in here. We're going to have it kind of nice and organized. I kind of like to have it as organized as possible. And we don't have any tuning in here right now. We don't have a set point, right? So let's come over here and put our set point. And I'm going to put this tag as PIDE set point. Just give it a basic name. It's going to be a real value. All right, so now that we have our set point in here, we're going to give it a set point. And again, we already talked about the set points are going to be, if you look at these set points right here, 0 to 100. Now we can change that if we want to. We want to say set point as the low would be like 60 and the high would be like 90, right? If we wanted to do it something like that. For the sake of what we're doing, I don't know, it's kind of fair to do that. Or we can do, what we can say this is like a cooling system or a heating system or something like that. So we can do like maybe even 50. All right, so then that equates to the set points, if it's out of that range, we're not going to be able to use it, right? So we'll just put 55 in here to begin with, and immediately it's not going to work, right? So we already know that. So I already have a PLC program that's inside of this processor. So I'm going to download this, and you're going to see a lot more, you know, of kind of the ins and outs of, like I said, setting up how you do things, auto tuning, and getting the full spectrum, right? So we did the level simulation last time. And this is all about loops, right? This is all about PID loops and understanding PID loops, understanding the process behind it. And when I say PIDs, PIDEs are that's what's taken over, right? So just know that PIDs were the old, right? PIDEs are the new. Okay, so we don't have any tuning in here yet. Obviously we're in manual too. So if we throw it in auto, well, basically it changes states right here. You can see that it's in auto, but it's not going to do anything because we don't have any tuning. We don't have any proportional, integral, derivative. Now we can change our equation type from independent to dependent real easy by clicking the little button, and we're going to keep our control action as our error is going to be basically our set point minus our PV. So it's going to be our set point minus the PV. And we're going to keep that just because, I mean, I think that's the simplest process for you to understand and for me to explain. With that said, we cannot come over here and go into auto tune, acquire the tag, put the tag in auto tune, and let's just say if we're in temperature. So if I said, no, let's just go 90 and then 5% change. We'll do a 5% step change of the CV with the PV change limit. The limit that the PV can change is going to be 90. Why did I do that? Because the set point that we currently have in our set points cannot exceed 90, right? So we have to hit apply. And if we try to auto tune right now, it's going to fail. And it failed because it's an invalid mode. Why is that in invalid mode? Because we still have it in auto. Okay, so we put it in manual. Go back to PIDE, our parameters in auto tune, and we go to auto tune, and then we hit the OK. Now, granted, this is going to take a little bit of time, and the reason it's going to take a little bit of time is because there's two things. When it comes to PIDEs and understanding that, you have your loop timing, which is going to be your task, and then you have your lead lag, which is what we're simulating. Now, if you would have seen that, what it did is it did a little bump test. So I'll show you that in just a second. Okay, but let's just put it as slow right now, and we'll set the gains. And we'll close. Okay, so now we have gains in here. But I'm going to show you that a little bit differently because realistically you need to see that. So let me see if I can't get it over here and do that a little bit differently this time. So with the CV step change, okay, the limit I'm putting that at is going to be the step change that it does. Okay, so I could put 10, it will step change to 10. If I put 5, it's going to step change to 5. This is based upon the percentage though of the CV. So you can go as high as low as you want to, but you got to be careful with it because it will go into a PID auto tune like fault. So just understand your limitations in that. So if you go to auto tune and we do a start, you're going to see the CV do a step change here in a second of 5%. And then when the 5% goes through, like it just did right now, it automatically goes to the dead time, and then the lead lag is going over and then fulfilling that PV. Now again, it gave the same parameters, so we could exactly what we had before, because it took a constant time. The time right now is 5.1 seconds, and the dead time was was actually 0.4 seconds. So we'll leave that like it is. I'm curious on why the dead time was so low on that. Let's see. We have our array, it can't be our array size. So let's look at time mode. Make sure I have that. Select time base execute mode. I don't believe I need this on. So, but let's just see. Curious on how this reacts. All right, so auto tune. Oh, let's get it to where you can see it. I'm sorry. I hit help on accident. So let's get it up where you can see it. So maybe I should take all this and move it back, but let's get it where you can see it again. Put all this right here. Auto tune brings it right here. See if that changes the lead lag or the dead time array. So it's going to step change to 5. Oh, it does says warning, observe PV change too small. Okay, and this is where you go into understanding your process again. So let's do 10. Hit apply. Try this again. It's in progress right now. So it's going to step change. When it step changes to 10, it immediately throws it out. And then we do our lead lag. So effectively, we only have a lead lag of, or we only have a timing of 1.5 seconds. And we're going to go put that in there. So now that we have it tuned, we'll just see how she reacts. And we'll put that in auto. And this is going to be tuning it to get to 55. Okay, so as far as our dead time and stuff like that, we need to work on that. But this is tuning it to, and this was basically the medium, right? So it should go right at the set point, maybe overshoot it just a tad, and then, but it looks like it's going to actually kind of go pretty well. Get right at set point and then stop. And that's just because it's only 5 seconds, to be honest with you. So, and looking at this a little bit closer, so we're tuning, our tuning is perfectly fine, but as far as our lead lag, our dead time, lead lag is working really well. Our dead time, we do need to change this timing mode back to 0. And as far as this, let's change the dead time to, because what happens is if your dead time is out of, if it's an invalid time, meaning it's outside of your array or something like that, then it's not going to work. So let's change this to 4 seconds. All right, so we'll come in here, we'll change the value, and let's just say 75 is our set point now. So 75 is our set point, and you see there was a lag in there, their dead time. So we're realistically, why it didn't work at 12 seconds is because we were out of our array. So, and that does happen, right? So just keep that in mind, and I'll tune it again just to show you that. But just so we're aware, you know, you have to understand the attributes of timing when it comes to a PIDE. And sometimes you can manually make mistakes, just like I just did, or, you know, when it comes down to it, you have to understand your task rate. You have to understand, you know, like what timing do you have in your lead, your lag, your dead time, your attributes as far as your PIDE loop. Okay, but you do see that it is tuned properly, right? Now when it comes down to it, when we throw it in manual, what that's going to do is it's going to settle out, that's settling out that PIDE loop, right? So meaning it's going to keep it at a constant. So it's not going to let it like control itself or kind of make adjustments, and I've done this before in several videos in the past, is basically made a trend of this, and in the trend it shows you that little bump that it does. So we're going to tune it again, and I tell you what, we'll change this from independent to dependent. So I want you to note that too. You see that how it goes from the integral goes to 1 minute, and then you go to minutes down here, and it goes to minutes repeat, and then it goes to minutes. So we're going to do dependent this time. Okay, keep in mind we're going to keep the same exact thing we had. So we'll do a step change of 10. We'll keep the PV change at our PV maximum, our set point maximum, which is basically 90. We're going to hit apply. We'll come over here, auto tune. We're going to hit start, and we're going to let the process take effect. Now it bumped up 10 just then, 85. Now the dead time is actually working this time. You can see that. So we have 4.3 seconds of dead time. Now we have 5.1 seconds of constant time. So altogether, we actually did have our complete 9 seconds. So you can see that that actually shows the tuning is much different. So the current tuning that I have in there is now the fast tuning. If I wanted it slow, I come over here, set slow, hit set gains, come over here, hit apply, change this back. Now I'm going to change this to, let's go to 90. Not going to change anything right now, right, until we go back to auto. Okay, so now it's back in auto, and it's going to slowly work its way up to get to the set point of 90. So we're going to watch the process. All right, so then we're going to take it down to, once this settles out, I think we should go back down to 55 or 60 and see how fast or slow it is. And you see that's much more, I would say, dynamic, you would say, because if the set point is 60 and the CV now is currently getting close to the set point, but it rapidly started, it like rapidly started getting there. And then as it gets closer to it, it takes away from that as far as the gains. So if we look at the gains on it, you can tell that the integral is very little. Now, to explain this again, what is the proportion, what is the integral, and what is the derivative? Proportion is basically your foot on the gas, right? Integral is the time of your scanning. The integral is going to be like if you're not hitting your set point. If you're not hitting your set point and your PVs or your proportion is just not enough, it's going to slowly start adding to it based upon your timing, the timing of your task. So if I change the timing of the task, this is all going to change. And I want to show you that too, because it's very important. Like if I change this to 300 milliseconds, let's just say, come in here, 300 milliseconds. Now, I didn't change the name because obviously, let's just change the name so that everybody's well aware. So this is 300 milliseconds now, okay? Now, in all fairness, I need to retune this, okay? The reason I need to retune it is because the scanning of the process changed. So I'm going to come over here. I'm going to show you the same exact thing I did before. I'm going to auto tune it. Come over here. We're going to auto tune. It's going to change at a step change of 10. And we might want to bump that back down to 5, to be honest with you, but it's going to step change to 10. And once it step changes to 10, and again, you see that was much slower because we're at 300 milliseconds. Okay, so that's much slower reaction. So the tuning is just completely different on it, because we basically are now 3 times different, right? And you can see the range in there, right? So if we do slow, put it in here. Now what we can do is in the step change, we can change the step change to 5, back down to 5. I think that's adequate, right? Let's do a process change of that. Go ahead and tune it for 5, and that's going to do a minute little change, a step change. So right now it's at 60. It should go to 65, and then it's going to start calculating its process, right? It's calculating the auto tune gains that it needs. This is why I like auto tune so much, but also too the lead lag and the dead time and stuff like that. It's very effective. It's very effective to teach, very effective to learn. It did observe that the PV was too small, so might need to bump that up a little bit, but you do see the dead time, constant time, dead time right there. And so let's change that a little bit. Let's put this at 7 and see what that does. So this is just showing, again, like going through, understanding tuning, understanding the timing. I have no doubt that the tuning that was in there, that just came up and said that there was a small issue, that it would have worked. I have no doubt that it would have worked, because it would have. The thing is you have to look at your task and your scanning of your task. So the step change for your task was a little bit wrong, and the dead time you see changed right here. We didn't have any problems on this one, so we're going to go slow, set the gains, come over here. We're going to put this at 90 again. Okay, and then we're going to come back and put this back in auto, and then we can watch the progression of the actual tuning at this point. Now, again, you can see it rapidly change, and then you can see it slowly start backing off. And the reason it starts doing that is it says, okay, the proportion is this. And if the proportion is too low, then it's going to add the integral. Now the integral is based upon the scan rate, so it's going to add to that, and that's what it's doing right now. That's why it's slowed down. Now the derivative is put in there to slow that down even more. It's like hitting the brakes. So if you think about it like that. So just keep in mind, the auto tune is very effective. 90% of the time when you're using, if you're manually tuning something, you're probably not going to put derivative in there. You're just going to go a PI. But you see right now the way it's approaching 90, but it's approaching 90 so slow that it will not overshoot. And again, that's where that derivative comes in play, because it's backing it off, saying, well, we're close enough to it, but we're not, we still need to get there, right? So it's adding integral and using the derivative at the same time, and it will finally get to its set point. So you can see that it's slowly getting there. It'll finally get to 90, and this is what I consider like a big loop. Like you would have like a big loop, and you're trying to really control that to a real specific, right at set point type deal. Now sometimes you can't do that on things that, like, if the pump is real close to the valve, and the valve is a control valve, 4 to 20 or something like that, 0 to 100%. Like if you got something real close together, it's really hard to do that. Or if you have like a variable, like your thickness of your product is changing or something like that, it's like your viscosity of your stuff is changing, you're going to have an issue with that. This is just tuning and getting the understanding of tuning. So let's go ahead and change this back down to 60. And you see it's going to rapidly move. And then when it approaches 60 and it gets in the 60s, you'll start seeing it slow down. And that's because of that very fact that I just explained a minute ago. But again, when it comes out to it, if you tune it for one thing and the viscosity of whatever you're running, let's just say you're running mineral oil one day, and then the next day you're running like maybe a thicker mineral oil, like maybe you change vendors, you may have to retune that loop a little bit because the viscosity changes. If the viscosity changes, then it could change the flow rate. It could change all kind of things. If you have a flow meter involved, it could be something just that simple, or it could be something like, you add, you're adding things together, and the thickness of the product got either less or more than it was before when you tuned it. Then that's more of a dynamic tuning, right? So you can throw parameters in there and kind of do that way. But this is, again, going back, showing you the basic understanding of like a lead lag, dead time, why you would use that, not for your process at all, but to simulate a process. When you're simulating a process, you're doing that to understand your attributes of what you're doing. But you need to understand too, is your viscosity of your product going to change? Is your thickness going to change? Is your throughput going to change, right? Is the, how much is going through the pipe or whatever the case may be. And I'm looking at this like it's a flow going through a pipe or something like that. It could be that you're doing this for temperature, and the temperature is always, maybe the temperature is going to change because of it's out in the atmosphere and there's no climate control, right? That could be a big factor in this. So you got to think about all these attributes when you're thinking about tuning a PIDE. Now, a lot of people are going to miss some of what I'm saying here because, this is a longer video and a lot of people did not hang around to watch every single detail of the video, sadly, because, again, the attention span of YouTube is not as great as it used to be. But if you're trying to learn, and you're trying to really understand tuning, you're trying to really understand how a PIDE works, you're trying to understand the base understanding about it, this is very, very important. Again, you can do this yourself. I'm not doing anything that I showed you how to build this from scratch. So you see it's right at 60, everything's working good. We can actually come in here and change the parameters. Like if we want to change the tuning, we can come over here to auto tune and just make it run a different. See, it's already pre-tuned. All we have to do is just change it. So in this atmosphere, let's put it at 70 so you can watch it go to 70. And you see kind of overshot a little bit. And then it comes back down. And then so you see that there's a difference in there. That's why I like to choose slow, but it all depends on the process that you're using. Sometimes you want to overshoot a little bit. There's nothing wrong with overshooting. But when it comes down to it, you have to understand your process. Understanding your process is the 100% key to success with this. So again, auto tuning, and again, I'm going to put it back at slow. Do the same thing. I'm just going to raise it by 10. And you see that it did not overshoot at all. So again, I go back to the same premise. You have to understand your timing. You have to understand your processes, your devices, your viscosity, your it doesn't have to be viscosity. It could be the attributes of whatever you're trying to control. It could be temperature. Is that inside a control atmosphere, like a temperature control atmosphere? Is it outside in the elements where it's cold one day, hot one day? Is there things like that in play that you need to understand? If it comes down to it is a viscosity or a fluid or something like that, then that does apply, right? It's very understandable that the thickness of the product will affect the loop. So understand the timing and the PID loop and the attributes, what type of devices, pumps, pump curves. You have the length of the piping, the control valve, how fast the control valve works, and this all applies to everything that we're talking about here. So when people ask, well, how do you tune a PID loop? This is how you tune a PIDE loop. It's understanding every bit of the process that is in play. Now, I've worked on a lot of Rockwell technicians and engineers in the field that are very, very good at what they do, and they do not use auto tune. They just manually tune everything. But again, they're used to everything that they've been working on, and they've been working on that stuff for, like, they could have been working on that project for at least a solid year. So you're not seeing, when you see them just manually tune it, you're seeing the right then, right there. And you think that they just know right off the bat what to do. They actually have the experience behind it because they have had to build that process. So when it comes down to it, I just want to add some clarity about this because, again, this is a longer video. But when it comes down to it, the longer videos give you that clarity, give you that depth, give you that knowledge. It's really, even if you have to watch this a couple times, even if you have to watch sections of it and come back to it. And like I said, the point of it is learning and getting it and comprehending it and really retaining that knowledge. Like, there's zero reasons why we at this age, you know, in technology, that we should be holding anything back. If what I teach doesn't make you better than what I am, then I'm failing at teaching. So this is why I'm slowing down in 2025, and I'm making these videos to make them more in depth. I know they're longer, I know they're harder to watch, but just hang in with it, watch it, come back to it, watch it again, try it yourself, implement it yourself, and watch what it does. With that said, hopefully you learned a lot from this video. See you guys on the next one.